I'm Subram, and I'll start with the neural optimal transport paper. So, just a brief about what the paper discusses. It proposes a novel algorithm to compute the deterministic as well as the stochastic optimal transport plans using neural networks. The other thing the paper proposes is the weak and strong optimal transport costs. Um, with that, it also gives a proof why the neural networks are universal approximators of the transport plans. And lastly, I'll just touch upon the evaluations performed through the algorithm. So, majority of the existing methods out there uses the optimal transport cost um, as a loss function for the generator networks. But this paper introduces a different uses of this called the OT transport optimal transport plan, which is being used like a generative model for, and it gives better performances in practical tasks. It also it mainly focuses on the optimal transport plans. So just going through the notations, here just x, y, z means the Polish spaces, whereas p, x, p, y, p, z means the respective probability distributions on them. Another important notation is the pi of p comma q, which means the set of probability distributions on the marginals of p and q. And there is another push forward operator here denoted, where p push forward say any space x gives the output distribution y. So coming down to the proof of why the why the neural networks are a universal approximators of the stochastic transport maps. So given the source distribution p over the space x, a noise distribution over z, and the stochastic map which I discussed earlier, t, given the noise and the input distribution, which push forwards to the output distribution y. It tells us that we can, for a small epsilon which is greater than 0, we can find a neural network t theta, which does two things. One is the function approximation, which basically means that our transport map and the original transport map would be approximately similar. And the other is the Wasserstein distance between our transport map function and the transport map distribution and the output distribution would be also similar. So coming down to the proof of it, firstly, the step one would be to see if the squared L2 norm of the transport map is finite or not. So here our T, which push forwards to Q, which push forwards to Q, and if we plug it in the original equation, we can find that this is a finite second moment, because we have previously made the assumption that our output distribution would be finite second moment, and this would give us that our transport map would be finite, and this would be this would prove that the square L2 norm would be finite. Secondly, we would have to prove that continuous functions are dense in L2. For that, since we already have proven that T is in the L2 space, and for any epsilon, there would exist a continuous function such that any continuous function minus the original transport map in the L2 space would be approximately similar. And the last and third one would be the neural network that would be dense in that continuous space. For that also, if our transport map minus some continuous function g in the L1 space, if it's approximately similar, then over the compact space, if the region is finite, L1 convergence would imply the L2 convergence, and that's we could then imply that our transport map would also be similar to that, to the continuous function.
Are there any So the neural network here, there's no assumption on the capacity upper bound.
Mm, upper bound is in?
I mean, what is the number of parameters in neural network? No such assumption.
No, not right now. I guess. In the there is an evaluation where they have told that unpaired translation image to image task. They have told that the parameters are far less than the papers which have used GANs as their neural network. So they are far lesser than the papers which have used GANs. So just combining all the approximations, we can get that our approximated transport map would be approximately similar to the original transport map of the output distribution. So coming to the strong optimal transport formulations. So firstly, with the strong formulation, which was given by Monges, so it was given very like in the 1980s. So given the probability distributions P and Q and the cost function, so cost functions tells us that we how much it would cost to move some mass from X to Y. So the cost function would be reducing the cost given the input distribution and using that transport map um, to transfer the mass to Q, and we would minimize it basically. So, but this OT formulation it's very restrictive, as in since we are moving masses to masses in a pointwise manner, there might be no transport maps available for them. Also, one other thing is Monge's cost is not symmetric. Moving P to Q and Q to P are two different things. And this is a thing I told. It's a deterministic transport. So every mass X is deterministically moved to Y. And so there is no mass splitting, and it is very restrictive. To come out of that, there is a relaxation given by Kantarovich, where now instead of a single point Y, we are taking the joint probability distribution over X and Y. And here we have just replaced the previous point masses to the joint probability distribution. And now we are saying that a pi star would be the optimal transport map, which would be the probability distribution between P and Y, joint probability distribution. So here just we would note that since the point masses can be spread across now, so the mass leaving from X should add correctly to the distribution P, and similarly the mass arriving at Y should add correctly to Q. Lastly, this is a more relaxation of the strong OT formulation given by Gosselin. This was done in 2017. So now, since we were dealing with just the probability joint probability distribution, here he uses another. So instead of the joint probability distribution, we should use the whole distribution where the mass goes. So instead of that cost X comma nu, we are using a conditional probability conditional distribution where given the input distribution X, we are taking care of the entire distribution and then computing the cost function and then minimizing it over the entire joint probability distribution. So yes, so this is just the weak OT map is just a special case of strong OT map if we take in account the cost function which was given in the previous slides. If we put up we plug in the cost function, we would get that this is a special weak strong OT is a special case of weak OT. And an example of this is given by Wasserton, where the cost function is something like this, where the first term sees if the input distribution is closely related to the output distribution, whereas the other term where the gamma is there, it uses this as a stochastic transport plan, where if we increase the value of gamma, we see that the diversity increases, whereas the similarity decreases between the images. and this would be in the evaluation part. I discussed it further. Yes.
System ensures that you are not studying in the arbitrary. So you ensure that the distributions are kind of separate.
Distribution in X and Y.
So the diagram,
Yeah.
see overlap on how do you minimize the overlap? Minimize the overlap or do you want to have?
I don't think so. Anything is written in the paper as.
What do you think?
Even if there's an overlap, I don't think so. There would be a problem. Mm, I guess the in the later slides we have the dual problem relaxation where this case is handled probably. So, yeah. So coming to the existence of the transport plans. So is it possible to always get a optimal transport plan? These three conditions need to be satisfied. One is the lower boundedness for the cost function. Second is the convexity approach, and the last is lower semi-continuous, suggesting there is no sudden drops for the gradient descent to continue. Now comes the main part, which is the duality. Since we are minimizing over the cost functions, it would be a complicated task for neural networks to do. So instead of doing that, we would use the optimization of dual form, where now we have a potential function and something called the weak C transform of f, which is defined like this, where we have the cost function, and given the potential function, we integrate it over all the output distribution, and this is how weak C transform is defined, and we plug it here, and then this becomes the dual form, which is then used in the paper. So so at the last, it comes down to see if we get the optimized potential function, it comes down to the integral of the cost function. So it is proved that it becomes the integral of the cost function.
There's a potential function in the three.
So it's a potential.
F is a potential function.
This is a F is a neural network.
And there, I mean, somehow something is wrong, missing here, right? So in three, where's the potential function? I mean, where?
No, 3 was just the OT formulation. From that, we derived the dual form.
Where are the marginal constraints? Constraints of the marginals. That is at pi p.
Yeah.
And I see. So there are constraints on P and Q, and those are reflecting in the dual in the form of potential integrations of the potentials on P and Q. But then, isn't something missing in 5? What about the cost itself?
Cost.
Acha.
Yeah. So we plug it here.
Sorry. Yeah.
Yeah, it will come later.
Sorry?
Min max.
Yeah, it's min max.
Yeah, it will come later.
Okay.
So now we'll reformulate it. So basically, we have the C transform function, and now we would plug this push forward distribution here, and we would get this as a new C transform function. So yeah, this is that we weren't using the probability distributions which of the OT formulation because it was infinite decimal and it was hard. Sorry, reformulation as in so now we would plug in this push forward distributions and we would prove that the whole dual form, if we get the optimal f star, it would be equal to the integral of the cost function. This, so basically, there wouldn't be any all of these stuff, the functions. This would cut it out. Okay. So yeah, this is just a derivation of what happened. The new we plug it the push forward network, and then this push forward is then change with the change of variables. We plug it in the main function, so we would get the C transform integral. Now coming to the integration of the C transform. So instead, like instead of computing it pointwise, we use it with the noise distribution and minimize it over the whole transport map. So here the T x comma z, where x is the input and z is the noise distribution. This is done as a neural network, and then we train it using stochastic gradient descent, and then push noise throughout and get. Yeah, in somewhere they use noise, different noise distribution, as in the same network, different.
Yeah, in the same network, different noise distribution.
I don't think so. Like in the evaluation.
Gaussian processes.
No. In the, they gave an example of just the Gaussian. They use Gaussian and then evaluated it. So yeah, coming to the max min formulation of that. So here the potential function f tries to maximize the objective, and then the after that the transport map tries to minimize the objective and find the stochastic transport maps. So an analogy of that using GANs would be f would be like the discriminator, which would make the transport map expensive, like getting the difference between the generated outputs and the original outputs, where T acts as the generator and tries to fool the potential function. Next. The lemma 4 says that if we get maximizer f star, would we get the stochastic map T star given f star? So for that, in the algorithm, we use that we first learn f star, and then for every f star we learn T star, and this is the proof of that. So, given the f star, if we plug the transport map, we would get this equation, and if we plug it here, so this term gets cancelled and we would get the original cost of the distribution. So this is the entire algorithm where PQS is PQS are the distributions, the mapping network, transport map, and the potential function, the number of iterations, the cost function, and another cost function for the transport map. So this is the loss function where we are averaging over the input. Then for each input, we're averaging over the noise function, sorry, the noise distribution, and then we are getting the potential function as the optimized potential function. And for every potential function, we are then calculating the transport loss, where over every x, this is the transport map for that particular cost, and this is the we are plugging it the transport, and then we're calculating the loss and updating it. This is just an overview of what I have told previously. So just f of omega would be trained to maximize the dual objective, where this is using to minimize. So coming to the evaluations, so yeah. So when gamma is 0, as I told, it's almost similar. There is no variance as such. Whereas for 1 and 2, there is some variance. There is some variance here for 1 and 3. And the last one, the variations becomes high. These are for toy 1D and 2D experiments where this is the input and output, and the learned is almost similar to the output. And this is the maps given. Similarly, these are the original maps, and this is almost corresponding to the one. And this is for the toy 2D where the target and the fitted distribution almost matches. For unpaired also. So one thing is for deterministic one-to-one mappings, most of the previous approaches are almost similar, whereas one-to-many approaches, NOT performs significantly better than the other ones. Whereas given the domains are different from one another, NOT performs significantly approaches. And here, NOT is just pure hypermedia compared to others. And for evaluation, they have used the FID score, where the lower FID, the better.
Hello. Hello. Yeah. Hello. So this is generative modeling with optimal transport maps. This paper is published at conference ICLR in 2022. Yeah. So basically, this paper's aim is that basically the optimal transport is used in GANs to while calculating the cost while training the GANs. But this optimal transport can also be used to generate the basic map can be used to like can be used to generate it can be replaced using a generative model. So basically in GANs we use this Wassertian 2 distance to find the cost of the generated image and the fake image. Like the fake image is generated image and the exact image. So basically here the optimal transport can be used just the research has done like there are so many papers which has published finding that cost and utilizing it to train, but here the exact map can be used to generate. This paper discusses mainly about that. Yeah. And there are applications as well discussed about denoising, colorization, and inpainting. Next. Yeah, and basically about this GANs, we use Wassertian distance, which enhances the diversity, convergence, and training stability. Whereas using OT as the loss function, it typically it is used to as an objective to train the generative model. And yeah, and mainly this one, the latent space, this OT cost was used in latent spaces, that is in the autoencoders, but in the high dimensional settings of decoding is often inaccurate and it gives poor results. But this paper discusses about that as well. Next. Yeah. So this paper gives an end-to-end algorithm to train the OT maps under W2 cost, and there are applications as well. Two applications. One is of image generation, and another is unpaired image restoration. Yeah, as told already that it avoids autoencoders and works directly in the ambient space. And it also concludes that the results are almost comparable to the OT based models with better interpretability. As this is already discussed by Subram, I'll just brief about this. Monge's formulation of the optimal transport, basically it has a limitation that it maps point to point. The points in X are directly mapped to the points in y, but basically if suppose we have a mass distribution of x and that points to various points in uh, the output set, that's a limitation that is covered by the next methodology, Cantor's relaxation. It basically it breaks down that mass distribution of x and then it allots points to the in y set. Yeah, and this is the previous one. This is Kantorovich. It solves that limitation of the previous methodology. It basically breaks down that entire mass distribution of x and then it allots the points to y.
You have distributions on each two cells or single cell. Is this direct V-code direct follow-up of V-code?
No, I'm not exactly sure about that, but this is how it was presented in this paper. Yeah. Next. And yeah, duality, basically the previous methodology gets complex to solve the optimization problem in this context. So this duality is used to basically break down that expressions, and then the cost function, whichever we get, it's basically relatively easier to solve. And primal dual relationship also helps in this context. Yeah. Yes. And then yeah, here basically this here there are two cases basically. So the optimal transfer generation model has two cases. One is that uh, both the images, input images and the output images have same dimensions, and another case is that both input and output have different dimensions, basically equal dimensions and unequal dimensions. Before that, there were two cases, as I told. The OT can be used in generation, firstly as the cost, and secondly as the map itself. The generative model map can be replaced as OT. So this is how it is used as the cost function. The OT is used as a cost function. Here's the basically it replaces the Wassertian distance, which is mu theta. Mu theta here is the generated image basically. If I talk, this is mostly about images. So mu theta is the generated image, theta based on theta parameters, and mu is the original image. So the Wassertian distance between these two is given by this expression, and this is duality based expression. Next. Yeah, as I told about now that OT is used as the generative map, here there are two cases. The both input and output have the equal dimensions and unequal dimensions. Yeah, here basically that not in this research paper, but before whatever the research papers were there, mostly they were. No, nothing about unbalance was talked about in this paper. But this particular thing, it wasn't there. So basically the research papers before this, mostly they were working on the latent spaces like inside autoencoders, and that was the performance there was very poor. And this paper basically has high dimensional data images. Next. Yeah, so the first case, equal dimensions of input and output distributions to learn the optimal maps physically. So here x and y both have the three-dimensional, and we consider here the Wassertian 2 distance W2, and the cost function is basically the quadratic ground cost. C of x comma y is this expression. And here the main assumption of this paper is that they're assuming this plan pi star as that it is deterministic. This is one of the assumptions. And yeah. The second one is the unequal dimensions of the input and output. So basically here they're using an embedding. Q is acting as an embedding and mu is the input. So from the main our OT plan will be from Q mu to nu. This is the final output. And and author also says that they can actually directly combine those two to a new function G star, mapping basically G star to club both of these functionalities. And yeah. Yeah, and if the both the dimensions are equal, then it basically goes back to the previous equal dimensioned case, and we basically get the same loss function. Yes. Yeah, and here is the algorithm for it. For learning the optimal transport between unequal dimensions. Unequal, here X is the input that is of H dimension, D is the final output dimension. And basically here we train two networks. First one is that potential network and second is the generative network. And yeah, so basically we repeat for both of them. It's like basic uh, decent algorithm.
So where is this unequal dimensions being handled? Where is there a projection happening? So I didn't get the unequal dimensions. Where is it being handled? Is there some projection layer? I mean, can you identify in this?
There is embedding Q that is used here. That is handling the case of unequal dimensions.
But how is Q? I mean, Q can go berserk, right? Q can possibly. You need to kind of regularize Q, no?
That hasn't been seen.
In fact, I can learn a Q to just simply overfit. So that you have some training samples, right?
Yes.
I can learn a Q to simply overfit. How do you ensure that Q generalizes well? You understand my point? You understand the question? And what happens when we have equal dimensions? Then Q becomes identity. No.
Yes, it becomes identity.
So
that
everything
was
remains the same except that Q becomes identity.
Yes, so that is only.
Are you sure?
Yes, in the previous slide also it was shown that. Yeah.
Show that.
Embedding Q becomes identity if the same dimensions.
Nothing else changes.
No.
Okay. Okay.
Yes. Yeah, then there are experiments. First one is about modeling the noise distribution, generating images from the noise distributions. In this subsection, basically mu is a 192 dimensional normal noise and V is the high dimensional, mu is the high dimensional data distribution, the output basically. And mu has the size of W cross H with C channels, basically C are the colors. And if we have the grayscaled images, then we basically just replicate them to match the dimension scales. Yeah, next. And yeah, here is our OTM model, optimal transport model. Here the FID score of this is 6.5, which is very, very, considerable to the comparatively other models. It gives better results and yes, and this is the auto-encoded OT model, which many researchers were working previously. And yeah, this is comparably better. Yes. Yeah, this is
actual data augmentation. Was there any experiment they performed for data augmentation as part of the supervised learning task?
the data set which they have used was just the celebrity set data.
I understand that, but in unpaired image restoration, they were using data generation for image restoration.
Yes. Firstly, they degraded the images and then they distributed the data set into three parts, A, B, and C. A and B have 90K data sets and samples, and C has 22K. And after this experiment is done, basically they train the degraded images of A part and clean images of B part to train, and basically they test with the C part of the images. Samples basically, and they also get to a good result. You can see the next slide. Yeah, and basically the FID scores for this when compared with the C part of the samples.
So, but everywhere there, it seems to be kind of FID.
FID.
also used in extrinsic evaluation, some data augmentation for much more complex tasks and any task.
No, no.
Okay, proceed.
Yeah. Next. Yeah, these are the images which they've attached. Yes, that's it. And yeah, basically, conclusion is that only that the results match very well with the other GAN models. And one limitation is that here they have considered this embedding Q as the quadratic cost. And one more, yeah, that is the main limitation of this. Basically, that doesn't work to for all the practical problems. It's basically straightforward. Yeah, that's it. Yeah, Chetan will present.
First of all, a very good afternoon, everyone. First of all, a very good afternoon, everyone. My name is Chetan Jadhav, and today I'm going to present a paper which was presented in the ACL 2021. It was vocabulary learning via optimal transport for neural machine translation. So, next. So the basic motivation is that the techniques that are basically used for vocabulary selections are like the byte pair encoding, so which basically focuses on subword frequency. So, but what happens is, when it comes to vocabulary size, it empirically selects it, so with no theoretical guidance. So, in order to overcome this, so they came up with an approach called vocabulary selection via the neural optimal transport. So, basically constructing an optimal transport map. So, basically, which doing vocabulary selection basically overcomes, like it maps the character level distribution, character level frequency distribution to the token level frequency distribution. So doing this basically increases the blue score for the machine translation. So this is one important task. Next. So so the inspiration came from the economics, that was like the marginal utility. So the marginal utility was, so marginal utility is basically nothing but so the marginal utility for the vocabularization here, it is defined as the negative derivative of the entropy against the vocabulary size. So next slide. If you just look at the graph, so there is a trade-off between the entropy and the blue score. So as we as we increase the size, vocabulary size, so we see that the blue score firstly increases as the entropy decreases, but it suddenly decreases at some point. So in order to overcome this, so we are gonna use the margin utility. So experiment next graph. So if you look at this graph, so this basically proves that, so they have basically taken 45 language space, for which they have plotted the Spearman score correlation between the what they say MUV, that is the marginal utility for the vocabularization, and the blue score. So if you just see like 2/3 of the 45 language space are positively correlated with the blue score. So making that marginal utility is basically one of the factors when it comes to for the selection of the vocabulary size. So back. So this is defined as the negative derivative of the basically entropy versus the vocabulary size. So, and this entropy is basically
So negative
negative derivative.
Difference with respect to increasing the vocabulary size.
Yes.
Relative gains in entropy to the vocabulary size. That's marginal utility. It's like an information gain.
Yes.
With respect to the vocabulary size. So what is the hypothesis? What is the main?
So basically, it focuses on like how vocabulary size basically is important when it comes to neural machine translation. So we'll just go to the objective part.
Yeah. How does marginal utility correlate with their final objective? So you're trying to maximize MBT.
So this margin definitely no change.
What's the
So
objective?
so usually what happens is that high MUV basically indicates that there is it is difficult for this. So what they have done is, so they have taken the bird model, so they have masked it, so they are predicting each and every word. So they are predicting each and every word. So now higher the MUV, so that basically indicates that it is harder to predict. So harder to predict that sentences. So we have to choose those words in the vocabulary, so which are harder to predict. So it will be easier for the model when it comes to the translation. So it will be easier for the model to focus on that part. So that is what their focus was on.
That is fine. So their objective is to what is the objective function?
Objective function. We are maximizing basically the marginal utility for the. So final, there is a final objective function, so which comes after like deriving. So it can be like it is like if you just okay. So
just why don't you continue from where you were?
okay.
So you'll come to it.
Yes, sir. So firstly, so firstly, if we are trying to maximize the marginal utility here. So now firstly, the marginal utility as far as the as it comes to the definition. So this V of t is basically nothing but the set of the vocabulary sizes of which has the maximum upper amount of S of t. So that S of t is basically nothing but the incremental integer sequence. So why they have taken this incremental integer sequences? So since the vocabulary size can be discrete, right? So they have taken some kind of sequence. So they are gonna iterate to this sequence for finding the optimal vocabulary size. So now for the entropy, so for the marginal utility, so it can be defined as this entropy, that is HV of t minus HV of t minus 1. So this is basically nothing but the entropy that has been calculated in the set of vocabulary sizes ranging from 0 to S of t. While the HV of t minus 1 is nothing but the set of vocabulary sizes ranging from 0 to S of t minus 1. So that is what this basically means. So if we go to the next slide, so they have applied some kind of relaxation. So they are telling that since the search space is kind of exponential, so we have to since we have to look for all the possible pairs. So they have applied relaxation and they are trying to optimize the lower bound. So since we know from the previous slide, this was the objective function, right? So now once we apply it on the lower bound of it, so we get this max of this. So now we are trying to find out the solution. Now this whole solution can be split into parts. Now we are trying to focus on how now ultimately we have to optimize to get the maximum entropy. So now if we further again analyze this, so now entropy definition is like here P of I, which is nothing but the token frequency, the words, and LV is nothing but in order to normalize it. So each word can be of different sizes. So we have taken the average length of the token here. So this would be the entropy. And if we just come down, we have further applied the relaxation, and they have applied this relaxation saying that this one, the vocabulary containing the top S of t most frequent tokens. So they have taken one such one such vocabulary which contains the most S of top frequent words, like the top S of t most frequent words, and they are applying the optimization on this, working on this. Next. So now again since again the search space is still intractable, so in order to avoid this, they are again applying more relaxation over it. So they are going to now from character, now they are going from token level to character level. So they are apply they have taken the P of I comma j to be the probability distribution. I have broken down into this. So this P of I log of P of I can So if I just write on the board, if you okay. So now this P of I, now we are just coming from token level, we are going into character level tokens. So we have just taken this single vocabulary, so which contains top frequent S of T tokens. So now that is T. So now again, this character level size is basically C, A, B, C, D, E, F, G. This all is basically fixed 26 alphabets. So now we are going to iterate over this. So we are trying to why are we doing this is we are trying to basically come to a point where this matches their neural transfer problem. So optimal transfer problem. So that would be this down like this one. So they have done it when they have taken the token level and the character level combined. So they are writing it as a joint probability distribution, and then they are breaking it down further. So this P of I, this can be further written as, since we already know like P of J given I. So D, they have like they have defined this minus log of P J given I. So this.
What is the target? This is what is the target? So,
so like if you just take the character level tokens A, B, C, D, E, and then you have the token level tokens that are the combination of this, right? A, B, B, C, C, A, and this one. So now what you're trying to do is like we have this A, B, C, and we are trying to get the vocabulary size, get a vocabulary having A, B, C, A, B, B, C. So, but not all, just the most, like just the ones which are having the maximum entropy. So that is what we are trying to do. Okay. So they write it as a joint probability P of I comma J, and then they have taken this conditional probability P of J given I. So that is basically nothing but P of I comma J upon P of I. So then they have written this P of I in terms of P of I comma J, and then this one is basically nothing but the entropy of the joint probability distribution, and while the other one is basically they have just named it as D over there. And
so the optimal transport is really between some m grams and n grams.
Yes,
M grams are basically 1 grams, and n grams are bigrams. Bigrams are.
So mostly in the paper they have taken up to like they are splitting it. So they keep on merging it. So first they take the words, split it in terms of character level tokens. So in the vocabulary, so which vocabulary they have taken. So suppose they have taken the size of 100K. So they have certain size, right? So they have this ABC words. So now if these words are not in the vocabulary, they are splitting it. So that is how they keep or they merge it. It comes in the algorithm part, so I'll explain it there. Setup of. So now this like so this is some type of constraint they have put on the like D of I comma J, we have defined it. So since we know that what is P of J given I, J is nothing but the character and I is nothing but the token. So what if the character is not in the token? So for that they have taken it as plus infinity, and for defining what is P of J given I, so that is what is the probability of that character being in that token. So they define it as minus log 1 upon length of I. So P of J given I. So then finally applying this constraints, that's this that they have defined this furthermore number. Okay, so what they are doing is now they have defined this transpose matrix, that is your P. So now they have applied constraint on it. So if you just look at the P of I comma J, if you just take the rows of it, so you get the probability of that probability of probability of that token, and if you just take the columns, you get the probability of that character. So they applied that constraint over which over if you go back, this one. So this objective function with this constraints. So they are trying to optimize it. So next. So for the implementation part, so first what happens is, so they next algorithm. If you just look at the algorithm here, so what they do is they take the sequence of token candidates L, they're ranked by frequencies. So now what they will do is, so L, as I told you that yes is basically the set incremental sequence, yes, right? So it has 10 tokens, 20 tokens, 30 tokens in some type of sequence. So now they have the sequence of these tokens. So now they are going to iterate over the each token size. So each vocabulary size, that is 10K, 20K, and this is different for bilingual and the multilingual. So then they use syncon algorithms. So what in syncon algorithm, what it does is it tries to like that U and V are basically nothing but the scaling factors for the syncon. So this basically ensures that the sum for converging. So we want the sum of the rows to be equal to the probability of that token, and the sum of the columns to be equal to the probability of that character.
Will it be a kind of cyclic dependency, because as you keep growing the source, the target keeps growing. The target actually becomes the source, right? So there's no clean separation, right, between the source and the target. Maybe the P and the Q, or P and the D over there. You understand?
No, sir. If you can repeat it again.
So token frequencies, PI based on D, CAR frequencies. So token characters remain the two P and the Q, right? Is that correct? Are they static or are they dynamic?
This P of T and P of C. No, sir, they will be static. So for the S, for different cases, there will be different tokens there. So there might be different things. So for a single S, for a single set of vocabulary, so they're computing the P of T and the P of C from there. So token frequencies and the character level frequencies.
Okay.
So now if you look at the results, so they have just done it for the different translation tasks. Firstly, for the bilingual translation. So this first table is for the standard vocabulary sizes. So if they have taken the BP, that is the byte pair encoding for the 30K vocabulary size words. So and the our that was nothing but the vocabulary learning using the optimal transport. So we can just see the blue score achieved was better, obviously, than the byte pair encoding. And also, if you just look at the time, like next, and also the computation type was significantly reduced. And if you just see for the byte pair encoding, it took around 384 GPU hours, and for the like for the optimal transport, it took like around 30 GPU hours. So next, so our project we'll be just trying to do a textile transfer using optimal transport. So here, so there's a research paper on it, sir.
I don't want to just call him out.
So still there's a research paper on it, textile transfer. So that basically from
why can't we use this for better tokenization itself?
Yes, so we can use it for that as
well. I mean, what's the best use of this? Should it be site transfer? Should it be tokenization itself?
I was discussing with the sir the other day as well. So he told me to do something in the field of natural language. So that day I came.
Collectively, I developed good understanding, but I personally believe it's very because problem with formal informal knowledge is very difficult to measure.
So there is something called like
curriculum learning will be perfect for this because you can use OT to determine, right? Similar tests. I mean, that is very easy. Easy and hard samples.
Okay.
I mean, real duplicates. Good real duplicates can easily come. I think that's the best use of your. I mean, collectively, a very good understanding of the space. Right? I think curriculum will be good. That's what you have discussed. Right?
Yes, sir.
You can measure it.
Okay.
You can measure it through class labels, etc. Okay.
So, sir, like we'll be doing then curricular training on this, like.
Yeah. So, I mean, the style transfer is too broad.
Yes, sir. Yes.
So, getting a generative space, getting something that can be.
So, actually, our motivation for doing textile transfer was so we basically in the previous course we fine-tuned our model for it, and we also developed a matrix for evaluating it as well. So, because we trained our separate model, So which give us the formality score after we have just done the formal to informal conversion. So that was our motivation for going TST this optimal transfer. But still, if you just insist, you will be doing curriculum training also because
Yeah, I mean, it comes close enough, but that's more measurable.
okay, sir.
So it's not very easy to measure.
Okay.
You can't measure.
Okay, sir. Got it. Thank you, sir.
Okay. So the curriculum part, you can curriculum. Four people. And here, so that guy has presentation.
He said that they are come on.
They all okay, so this entire curriculum may be an extrinsic measure. Intrinsically, we also look at classification, legal indicators, I mean, whether they have similar kind of complexity scores. It could be intrinsic measure of this, right? And it could be curriculum can be assessed when it comes to extrinsic, and whether they can use the curriculum for improving, let's say, pre-training of model. I would suggest they focus on that. Okay.
No. No.
They are very good at this. So I feel we should be put to good use. Okay.
Or like
Okay. Yes. Thanks. Good.